The Internet is a collection of interconnected physical and logical networks. It functions through standardized protocols rather than existing as a weightless, wireless entity. At its core, it is a global system designed to solve a single problem: how two computers at arbitrary locations on Earth can exchange information reliably. To see that engineering in action, we need to freeze time the exact millisecond a user hits enter on a specific URL. From this moment, we have roughly 50 milliseconds to track a request as it leaves a laptop, crosses the ocean, and returns a response, before the user even perceives a delay. For a developer, ignoring these internals is like a civil engineer ignoring gravity. Understanding this journey is the only way to see how software actually lives within its environment. The process begins with a translation. Humans remember domain names, but computers require 32-bit or 128-bit numerical IP addresses to identify a device's specific location on the network. The browser initiates a DNS lookup, querying a hierarchy of servers, from root to authoritative, to translate a domain into a routable IP. Then the data is sliced into independent packets that take different routes to reach the endpoint. Before these packets move, a TCP three-way handshake establishes a reliable connection through a series of synchronization and acknowledgement signals. TLS encryption then wraps this data to ensure it cannot be read or tampered with during transit. This combination of DNS mapping and packet switching ensures that even in a chaotic global network, data reaches its destination with its integrity and order intact. As the request leaves the home, it passes through a local router. The device uses network address translation to map a private local address to the single public-facing IP assigned by the Internet service provider. At each local network hop, hardware MAC addresses take over, physically delivering the data frame from one device to the next. The request enters the physical backbone, converting software protocols into pulses of light. These signals travel through glass fiber optic cables at 200,000 kilometers per second. For international traffic, this requires a massive maritime infrastructure. The majority of data travels through submarine cables laid across the ocean floor, forming the physical links between continents. Every wireless experience depends on this physical reality: billions of dollars in hardware and glass fiber resting at the bottom of the sea. When the request reaches the target network, it may be intercepted by a content delivery network. These distributed servers host copies of static files at the geographic edge, reducing the physical distance the data must travel to reach the user. Dynamic requests continue into the data center. These buildings are designed to keep thousands of servers running 24/7, requiring redundant power supplies and industrial cooling systems to manage the heat generated by the hardware. To prevent any single server from becoming a bottleneck, a load balancer distributes incoming packets across multiple machines based on their current capacity and health. The packet finally reaches the application server. The machine processes the request, queries the database, and generates the response data. This architecture relies on redundancy. By distributing the load across multiple layers of specialized hardware, the network maintains availability even under heavy global traffic. The response now makes the return journey. Once it arrives back at the user's device, the packets are reordered, and the headers are stripped away in a process called decapsulation, allowing the browser to render the final page. The OSI model is a 7-layer framework standardizing how hardware and software communicate. It provides a map for troubleshooting. A physical cable cut is a layer 1 issue, a routing error occurs at layer 3, and an application crash lives at layer 7. Engineers use these layers to isolate and debug issues. By identifying which tier a problem lives at, they can resolve specific failures without treating the entire network as a mystery. By tracking this journey from the ocean floor to the browser, the Internet's complexity becomes visible. It is a layered system of physical infrastructure and agreed-upon rules that make global communication possible.